Hi, in this video we're going to do some practice problems on our reaction mechanisms. First we have a two-step reaction mechanism as outlined below, and it told us what a slow step, which was a slow and which was a fast. Now what is the overall reaction? The overall reaction will be NO2Cl plus NO2Cl plus Cl, all the reactants, makes all the products, NO2 plus Cl plus NO2 plus Cl2. Now as you can see here, Cl and Cl cancel on both sides, so this can be rewritten as 2NO. 2NO2Cl makes NO2, 2 of that, 2NO2 plus Cl2. Second, is Cl a catalyst or an intermediate? Now, as you can see, it is produced and then used up immediately. So this is what we call an intermediate. Intermediate. In the rate law, what is the rate law for each elementary step? Okay, so let's find the rate law for the slope step first. It is really easy, just rate equals K times the product, which is NO2Cl. Fast is also rate equals K times NO2Cl, because the reactants is the same. So this will be, let me write it, NO2Cl. There. Now what is the rate law for the reaction? Again, in the previous video, we stated that the rate law for the overall reaction is the rate law of the slower reaction. So the rate law for the slower reaction is this one. So our final rate law is our rate law for the overall is rate equals K NO2Cl. Now, just a coincidence that it happened to be the rate law for the fast step as well. But when you get to another problem, remember to always stick with the slow one. The slow rate law is the rate law for the overall. Now be careful, don't mix it up with overall reaction like what I did when I was doing these problems. So overall reaction is all the products and reactants combined, but the rate law for the overall reaction is only the slow step. Next, we have the two-step reaction mechanism. What is the overall reaction? Reaction is when you add up all the products and reactants. H2O2 plus I minus plus H2O2 plus IO minus makes H2O plus IO minus plus H2O plus O2 plus I minus. Now first, we need to determine if there's any intermediate or catalyst. Now as you can see, IO is used up immediately after it's produced. So IO is an intermediate and they will cancel each other out. I minus and I minus are both in the reactant product as well. So you might want to cancel it, but be aware. Now I minus is the reactant in the beginning and the product at the end. So this is not an intermediate. Instead, it's a catalyst. And catalysts, we do not cancel out. Well, we kind of do, but we need to save it for later. So let's circle these, just to know that these are catalysts. Now let's rewrite the reaction on the over here. Alright, so we have two H2Os. No, sorry. We have two H2O2s makes two H2Os plus O2. And we're ignoring the I minus because we're going to write the I minus over here. That's where the catalyst goes. In any given reaction, if there's a catalyst, it will go on top of the arrow. And this is our final equation. Alright, identify the intermediate. We just did, it's IO minus. And identify the catalyst, we just did, it's I minus. What is the rate law for each elementary step? Alright, so rate is equal to, let's find the slow step. Rate is equal to K times H2O2 times I minus. Remember, just rate law, just rate times K times each of the reactants. And for the fast step, it's going to be rate is equal to K times first reactant, H2O2, times second reactant, IO minus. What is the rate law? Rate law for the overall reaction is the slow rate law, which is, we can just copy it. Rate is equal to K times H2O2, and in the first rate law, in the slow step, it's I minus instead of IO minus. Alright, and that's it. Final law number 6. We need to write the rate law for this reaction. Now this time we're given a bunch of data points. And do not be fooled by this, thinking you can just write rate is equal to K times A squared plus B. That is usually not the case. Now we'll have to do an experiment. We'll have to actually do some math and do some ratio cancelings, like what we did a few videos ago. First, let's find, we know that rate is equal to k times a to the some power times b to some power. Alright, we need to find that some power. So first, let's use experiment 2 and 3 to cancel out the a's. When we use experiment 2 and 3, we're going to get 3.0 times 10 to the negative 3 divided by 6.0 times 10 to the negative 3. Again, I'm dividing experiment 2 by experiment 3. The 0.20 will cancel each other out, and this will be equal to 0.2 divided by 0.4. These two, I know 3 divided by 6 will give me 1/2. Is equal to 0.2 divided by 0.4, also 1/2 to the nth power. So n is equal to 1. So b is to the first power. Now look for a. Now as you notice here, there's no two same values over here that can cancel each other out. This one we have to do a little bit more complicated step. So we're still gonna use two rate divided by each other. So this time let's use ratio. Rate 1 divided by rate 2 equals k times a times b. Now this time we already know b is to the first power, so we're not looking for n anymore, we're only looking for m. Down there will be the same. And we can rewrite this as 1.5 times 10 to the negative 3 divided by 3.0 times 10 to the negative 3 equals k, and k divide each other out because k do not change. 0.1 to the nth power divided by 0.2 to the nth power, which is these, times 0.1 to the nth power, which is this, and we find n as 1. Sorry, I don't need to write n anymore. Divided by 0.2 to the nth power, which is also 1. Now this is much easier to do. 1.5 divided by 3 is 1/2. 1/2 is equal to 1/2 m times 1/2. So we divide both sides by half to get 1. 1/2 divided by 1/2 is 1. 1 is equal to 1/2 to the nth power. And anything to the nth power is going to be, anything to the 0th power is going to be 1. So m is equal to 0. And this way, we know that this is 0. Find the rate constant k. Alright, perfect. We just use the rate law we just found. Let's use experiment 1. 1.5 times 10 to the negative 3 is equal to k times anything to the 0th power of 1, so we can basically ignore it, times b, which is 0.1. So we just have to do 1.5 e to the negative 3 divided by 0.1, which is 0.015. Now, what is the units? I'm going to write it onto the side again. That 0th order, 1st order, 2nd order, 3rd order. Alright. Unit for k. 0th order, it's m divided by time. 1st order will be time to negative 1st. 2nd is m negative 1st, time negative 1st. 3rd is m negative 2nd, time minus 1st, etc. What is the overall? K is dependent on the overall order. The overall order, because a is a 0, 0 plus 1 only makes it 1. So this is the first order overall reaction. And first order, we're going to use time to negative 1st power. What is the unit of time? It's minutes. As we can see over here, it's minutes. So our units will be minutes to the negative 1st power. 0.015 unit will be minutes to negative 1st power. Now, which of the following possible reaction mechanism is consistent with the rate law? What is our rate law? Rate is equal to k times b. So which of these has only one b in the slow step? This one, the slow step, is a plus b. So for this one, the rate law will be rate equals k times a times b. For the slow, remember, rate law for the overall is the rate law for the slow step. Now this does not match this. These two does not match. Over here, we only look at the slow step, remember? So the slow step will be rate equals k times b. And this does indeed match our rate law for this problem. So our answer is number 2. This one is a possible reaction mechanism that is consistent with the rate law, because the slow step, aka the step that determines the overall rate law, is consistent with our rate law. So after all these problems, the most important thing that you need to remember is probably that the reaction law for the slow step is the reaction law for the overall reaction. Let's do a few additional problems. So here it asks what is the rate law for the reaction. Again, rate law is the slow step, so rate is equal to k times a squared because there are 2 moles, and give 2 reasons why the above mechanism is possible. So why is this above mechanism possible? 1, because the mechanism is 2nd order for a and 0th order for B. As I said over here, it is second order for A and zeroth order for B, and our Rayleigh law supports the experimental data. Now our second one, mechanism has B in FASTAP. So therefore, changing the concentration of B wouldn't have an effect on the rate, as shown in our Rayleigh law. It does not have a B in it. Finally, number 13, elementary steps that involve 3 or more are very rare. Okay, why are experiments involving 3 or more reaction species very rare? This is because reactions need the molecules to line up in the correct orientation. It is unlikely that it would line up more than twice and still have enough kinetic energy. And that's it for our practice problems. Thank you for watching.